Okay, so we're now on to our next aspect of amounts. Okay? And we're going to talk about molarity in the conversation about amounts. A point here, we focused in previous sections on the composition of pure substances. Now we're going to talk about mixtures, right? And it's going to be basically concentration. That's what molarity is, all right? Similar to a pure substance, the relative composition of mixtures plays an important role in determining its properties. By relative, I mean how much of this compared to how much of that within the mixture, all right? So for example, if we have a cup of coffee, you might imagine that you can alter the amount of sugar that you have in there either by adding more spoons of sugar or by adding more coffee, right? And so that's gonna dictate the properties of the coffee, which is going to affect how you feel about it when you drink it, right? So solutions are everywhere in nature, and we talk about homogeneous mixtures, and that's what solutions are. It turns out heterogeneous are going to be difficult for us to appreciate or to evaluate. So homogeneous ones are the ones that are going to be most useful to us, and that's what we're going to focus our time. Now, the relative amount of a given solution component is known as its concentration. All right, so a solvent, you may know this, is the thing that dissolves the solute, okay? So the solute is going to be the minor component. The solvent is going to be the major component. A solution in which water is the solvent is oftentimes called aqueous. All right, so we're going to be calling things solvents and solutes and aqueous. We're going to be using these terms frequently. Good idea to write them down, but it's really more important that you use them. All right, so qualitative terms used to describe a solution are concentrated or dilute. In other words, sometimes we might just say, give me a concentrated solution of blank, and which means we've got, if it's concentrated, that means we have as much sugar in there as we possibly could get. Or if it's dilute, that means you can barely taste the sugar, right? So concentrated and dilute are qualitative terms, but we're going to be doing quantitative terms more often. And for quantitative terms, we're going to use, this is by far and away the most common one, moles per liter. That is to a chemist, right? Or the most common in this class, which is moles of solute per liter of the whole thing. By the way, notice this takes on the form of part per whole again, doesn't it? Right? Just like we've seen before many times. This is an SAT concept, part per whole. And molarity fits it. Moles of solute, that's the thing that's dissolved in it, per liter of solution, and that's the whole. Okay? So molarity is a useful concentration for many applications in chemistry. We care very much about molarity. It's going to help us a lot. So let's do an example. Example 3.14. A 355 ml soft drink, which is about 12 ounces, a 355 ml soft drink sample contains this much sucrose. You're going to die when you see this. Contains that much sucrose. What's the molar concentration? That's a lot of sucrose. If we did percent, you'd see, man, I don't want to drink that stuff. It does taste good, though. I won't deny. So a 355 milliliter soft drink sample contains that many moles of sucrose, okay? So the volume of the solution is 355 mils, but if I'm going to molar, I'm going to change this to liters, right? So it's going to be 0.355 liters, right, of solution, right? And if it's got that many moles of sucrose, then the moles of the solute equals 0.133 moles. Now, if I want molarity, it's really simple. I just do molarity equals moles per liter equals 0.133 moles per 0.355 liters, which is equal to, got to pull my calculator out here, 0.133 divided by 0.355, which gives us 0.3746 and so on. 0.3746 and so on. Now, this had 3 sig figs and that had 3 sig figs. So I'm going to have to report my answer to 3 sig figs. So this is going to go to 0.375 molar sucrose. All right, and that is how we calculate molarity. Now let's look at some other concentrations. Some other concentrations are, can you see this here? A little difficult to see. 5% acidity. So vinegar is 5% acetic acid dissolved in water. All right. Now, dilution is a process whereby we get the concentration that we want by adding solvent, which just is what you would expect, right? I'm guessing that term, if English is your first language, probably that's a term you've heard before. Dilution is where we simply add more solvent, okay? Dilution is a common way of getting solutions of desired concentration. What we'll do is we'll take a stock solution, which is really concentrated, and then we'll add enough solvent to it, oftentimes water. We'll add enough solvent to it such that it gets to the concentration that we want. For example, let's look at this sample of copper nitrate. So suppose I wanted this much volume of copper nitrate, CuNO3, okay? Copper nitrate. If I wanted, I think that's I think actually that's a copper 2 nitrate. It didn't say it here, but I think it's copper 2 nitrate. No, that's good. That would be green. So just give me copper nitrate, which is blue. So anyways, copper nitrate. Let's just say that's the name of it. So if we have this, if we want that much copper nitrate at a particular concentration, we can take our stock solution and just add water. Add water, right? And it would do exactly what you think. You see how it's darker here? It's because it's more concentrated here. Then we add the water. It becomes more dilute. All right, so we'll do some calculations for that in just a second. For now, let's just say that that's sort of conceptually what we're doing. We might do the same thing for potassium nitrate. We might take a solid potassium nitrate. Can you see I've got 4.75 grams of potassium nitrate, right? That's what that little label there is. This little piece of filter paper. It's about 3 inches filter paper. And there's some purple solid right on top of there. You can't really tell. It's purple maybe by looking at the picture. And let's say we wanted to get a particular concentration of potassium nitrate. So we would put it in this volumetric flask, right? We would dump that in here. And then we would add distilled water until we got to, and you can't see it from here, but there's a etch line. You might be able to see it barely. There's an etch line. Can you see that little line right there? That's what we do. For a volumetric flask, this is a very precise amount. This is 100 milliliters. This is 1 liter. And that's a nice way of making potassium nitrate to a particular concentration. All right, so let's talk about dilutions now. The amount of solute in a solution is equal to the product's molarity, right? Because molarity is moles per liter, right? That's what the M stands for. Oops, the M stands for moles per liter, and liters stands for liters, right? And can you see if I cross those off, I get moles? So moles is equal to moles per liter times liters, right? And so if I take this and I dilute it, so if I'm diluting something, I'm not doing anything to the moles in it, right? So in my initial, before I dilute it, it's N1. And then I add some volume, which takes my concentration down, makes it more dilute, right? But N doesn't change. So what I'm going to do is I'm going to say N1 is equal to N2 because I didn't add any solute, right? I just added solvent. And N1 is the solute in the beginning, and N2 is solute in the end, which they're the same, right? So that is going to say M1L1 is equal to M2L2, right? And this is my dilution formula. And that I can use when I don't change the amount of solute. M1L1 is equal to M2L2. And oftentimes, we don't write that as M1L1, M2L2. We write it as C1V1, C2V2, okay? So it's the same thing, and this is sort of a workhorse formula that we're going to use. This is for a dilution. Very important that we use it just for dilutions. So let's finish up this conversation with an example. Let's say we've got copper. Ooh, it was copper 2 nitrate. Oops, okay. I think, I don't know if that was what we were looking at earlier, but probably is, okay? See the copper 2 nitrate? All right, So it looks like we take this much volume and this concentration and we add water to it until it goes to that. So it looks like V1 is equal to 0.850 liters. V2 is equal to 1.80 liters. C1 is that 5.00 molar, right? What is the final concentration? What is the final concentration? C2 is equal to question mark. So I'm going to go, no problem. I got my formula, C1V1, C2V2. C2 then is going to equal C1V1 over V2, right? Where I just solve algebraically. Now I'm going to put my C1 in there. It's 5. I'm going to put my V1, which is 0.850, right? I'll worry about the sig figs in a second. And V2 is 1.8. And I'm going to calculate that, and then we'll decide how many sig figs we need. 5, clear, 5 times 0.85 divided by 1.8. Check my math, all right? Occasionally I'm going to get these wrong, never on purpose. But if I get something wrong, put a comment in the video, and I will correct it, or I don't know, ignore it maybe. So 2.36, I know my son's sitting right here. He was horrified when I said that. Sorry, son. I won't ignore it. I'll treat it like it's a very important comment. All right, this is what that is. All right. All right. So this number, how many sig figs does that number have in it? Well, it looked like it had 3, right? I didn't write all 3 of them, but it's there. How many does that have? Looks like that's got 3 also. And how many has that got? Looks like it has 3 also. So I'm going to have to report this to 3 sig figs. Okay? That means this number is going to be 2.36. And I round down because it's a 1 right there, right? 2.36 molar. And that is my answer. All right. Hope it's right. Get your calculator out and check it. And if I'm wrong, put that in the comments. All right. Hope this is helpful. Introduction to molarity. Very important.